Hello and welcome to this first video tutorial of C++ QED, where I'm going to show you how to install C++ QED on a completely fresh Ubuntu 20.04 installation, how to configure the build, compile the test suite, and run the tests. This is the main page of C++ QED on GitHub. As you can see, the default branch is the development branch, which has been passing all the tests again since a few months now. And the URL of the clone URL can be found here. I have just created fresh Ubuntu 20.04 machine in an OpenStack cloud environment, and we are going to use this one. It is called CPPQED bench. So first of all, we have to install all the prerequisites, different libraries that CPPQED depends on. We are using apt for this. So as you can see, we need GSL, the GNU Scientific Library, Boost, the Eigen library. We need CLang, which is the recommended compiler for C++ QED. We need Git, of course, to access GitHub, and we need CMake for configuring the build. And finally, the SciPy package for Python 3, which is needed for the Python front end of C++ QED, or it's rather a backend because we are using it for processing data that has been produced. Now for the sake of simplicity, we are installing all the Boost libraries. This is a bit of an overkill, but otherwise we will need to find out which ones CPPQED depends on actually. Which always changes a bit as Boost libraries get included in the standard library. Then we always like to use what is standard. So we migrate to the standard at that point. Okay, we have now all the prerequisites installed. So we are going to do a recursive clone from GitHub. It needs to be recursive because C++ QED also uses some modules, submodules, that are also hosted on GitHub. It's namely the Blitz library, which is still the fundamental data structure for the framework, and two pseudo-random number generators, the Xoshiro and the PCG. Okay, we have now all the code that we need from GitHub. As you can see, it's nicely structured into folders, the different tracts of the framework. We need to use here another branch because the development branch progressed a bit beyond what the compiler versions in Ubuntu 20.04 are supporting at the moment. It's chiefly because these new developments in C++, like C++ 17, some features are not supported on these compilers. So we need to check out this branch, Ubuntu 20.04 LTS. And now we are creating a build folder. I like to use build folders to contain all the builds, since in this way it's very easy to have differently configured builds in parallel in different build folders, like a debug build, for example, a release build, or builds with different compilers. And it's also very easy to wipe out a build if we don't need it anymore, simply by deleting the complete build folder. Okay, we need to configure the build, which we do with CMake. It's kind of a standard for C++ projects. We will use a release build type, which is the fast build type, not containing any debugging code, and the CLang compiler. Okay, apparently it has found all the components that it needed. So now hopefully we can build everything that we need for the tests. It is going to be a few minutes. This is a virtual machine with 4 cores, and we are using all the 4 cores for the build. Of course, with more cores, you might need to be careful, because the build can use a lot of memory. So you can have memory issues with many separate build threads. This is mostly because C++ QED is a very deeply templated code. It relies on templates and template metaprogramming heavily. The main design principle being that all the physical information which is available on the physical systems that we want to model with the different programs in the framework, the different scripts. So all the physical information which is available at compile time has to be optimally processed at compile time using template metaprogramming. So that's why compiling these codes is a bit heavy. It is already compiling the scripts, the highest level programs in the framework, which are situated in this CPP QED scripts folder, or these are the scripts that are permanently supported, but you can make your own scripts in separate scripts folders. Only a few more to go. For example, this ring script that you see here, it's meant to simulate a single particle moving in a ring cavity with two counter-propagating modes and interacting mechanically with the modes. Now a few more test programs are compiled. And finally, QED, which is the data processing backend, which allows you to read in quantum state data of quantum states saved by CPP QED scripts into Python and process them as NumPy arrays. And you can even prepare initial conditions from NumPy that CPP QED is able to process afterwards. Now we have everything to run the tests, so we are going to do that. It's also a few minutes. '85 test programs are available at the moment, but this list is continuously increasing. So we can see that all the tests pass. So thank you for your attention. In the next tutorial, I'm going to show you how to use scripts and interpret their output. Goodbye.